This is the fourth part of radio propagation modeling, an introduction, if you want to call it, to radio propagation modeling. And in the first three parts, I talked about coverage for the first part, and first in the free space. In the second part, I talked about coverage in the multipath environment, and then I told you that we can represent the coverage with distance power gradient to make our life easy. And then in part 3, I talked about the Doppler shift and calculation of Doppler shift, effect of movements. And I related that to another parameter, which was maximum Doppler shift, if you want to call it, which was a function of velocity times frequency divided by the speed of light. Okay? But all of the things that I did so far were narrowband signaling. Narrowband means what? Means that I was sending a cosine, and a spectrum of the cosine was what? Only an impulse. This time, we want to talk about wideband signaling. The widest bandwidth of a signal, or widest band signal, is what? Is an impulse. So earlier, what I had like, I was sending a cosine for narrowband. I was sending a cosine, a spectrum of a cosine was an impulse. This was the narrowband. Now I send something like an impulse, as close to an impulse. What is the spectrum of an impulse? Is very wide. Okay? Now, but I cannot send it like that. I mean, I send something like this, so the spectrum goes something like this. But a wideband signal, rather than this narrowband signal. Okay? Now, what is the difference? The first thing, I mean, just intuitively, I'm talking about multipath. I'm analyzing multipath environment. If I send like a narrow pulse, transmit, now, in cosine, I receive several cosines, and they add together, which would be, again, one cosine. So in narrowband communication, if I send a signal, I receive the same signal with different phase and amplitude. And phase and amplitude is moving a lot. But in wideband, if I send like a pulse, a narrow pulse, I will receive several pulses. These are pulses from different paths. They have different amplitudes, and they have different time of arrivals. Why the amplitudes are different? Because different paths are arriving from different distances. Why time of arrival is different? Because again, different paths are arriving from different amplitudes. But this time they are arriving separately. They are not arriving on top of one another. When it was cosine, because this is very narrow in time. But cosine was very like continuous, so they come on top of one another, and I transmit a cosine, I receive another cosine. Only the phase and magnitude is different. So in here, if I don't have any movement, if I have like three paths, these three paths stay very fixed with fixed amplitude. Okay? So this is like what we want to get into it. But this is very abstract. In reality, we have different things. We have different buildings, different environments, and different applications. What will happen to those? So now to go to this multipath, we want to see first what will happen to the equations. The impulse of the channel, impulse response of the channel, again is A0. This A0 is a square root of P0 divided by tau I times AI. This AI is like those reflection coefficients. And then this time I have an impulse e to the j phi I, the same phi that I had before. So I have the same phase, I have the same amplitude, But tau sub I is like really time of arrival of the path. So I have a bunch of impulses which are arriving. So if I want to now calculate the power, how do I calculate the power? This time I have several paths, several impulses. What is the power? Is power inside each of those paths, squared added up together. So in the old time, if I in the narrow band, I add all the phasors, then I take the magnitude of the total. In here, all of them is squared and added to one another, because there is no phase addition. See, if I have these paths, these three paths in here, each of them have different phases. But so what? Power of this is magnitude of this one is square. Power of this is magnitude of this is square. Magnitude of this is square. In narrow band, I had like one like this, one like this, one like this. They were adding together to give me total amplitude. And then a square of this total amplitude was my power. Do you follow? In here, this is this. This is this. This is this. But I don't add them like phasor and add them together. I just square them, add them together. Huh? So as a result, the total summation doesn't change with phase. It's not sensitive to phase anymore. Since it is not sensitive to phase anymore, what will happen? I don't have multipath fading the way that I had before. So my power, total received power, is more stable. But I don't have ideal. If I have ideal wideband, power is fixed. Okay? Because powers are added like squares. A square of amplitudes. But if it's narrow band, powers are phasors. They are going mumbo jumbo, which creates that fading. This is one basic understanding. It helps you to understand why, for example, people go to wideband CDMA. The only reason is not a stable signal. There are other reasons too. Wideband people go because they want to have higher data rates as well. But as you get wider in the bandwidth, your signal is more stable too. So you go to ultra wideband, for example, transmission, more or less you don't have as much fading. Okay? But for your cordless telephone, you have a lot more. If it's analog in particular, because analog is narrow band. When you go digital, always you expand the bandwidth, because you sample and send the signal. Okay? So the first thing is that we get this intuition that when we go to wider bandwidth, actually we expect more stable signal. Intuitively. The reason is that wideband isolates the paths. Narrow band mixes the paths. Make sense? If I have narrow band signal, it's like cosine. They come on top of one another and they add up. How do they add up? With a phasor. And this phase is changing very rapidly. So the signal, received signal strength, changes very rapidly. As I make my band wider, these guys are added up with a square of magnitude and they don't change as rapid. So provide but a more stable signal. Okay, I will show you some result. But if I'm in a moving environment, you remember that power was changing very, very rapidly for narrowband signal. Because of the phase. Okay, but if I have a wideband signal, they don't change that rapidly. So that distance power gradient that I had earlier will change too. Do you remember we had the 2-path model and 3-path models? The 2-path model, only I showed you the phase which was changing it. That was the phase which was shifting the gradient from 2 to 4. Now, if it's very, very wide band, the 2 paths, at long distances, they just add up. They just add up. Okay? But one problem is that if I go with this type, so then you may say, why not always I go to? Well, if you go to this such a wideband, very wideband, what will happen is that if you want to do communication with such narrow pulses, your pulses are going to interfere with the next pulses. Okay? So you will have the so-called inter-symbol interference. Okay? But for narrowband communications, you don't have inter-symbol interference. Okay? So as a result, practically, you cannot just blindly say, I make it wider and wider. But if I want to do channel measurements, I can do that with very wideband things, because I send like a pulse and I wait for it to die, then I send another pulse. But it's very slow and it's not bandwidth efficient. I have a very wide band, but I have a very small transmission rate. Okay, so basically, I mean, this is just introduction. In terms of intuition, what you want to know is that when you do bands, when you do very wide band, you're really isolating the paths. Isolating the paths. Now, how to use it or something, we will see it later on. Okay. Now, and as a result, the received signal power is going to be more stable. Now, let's see that. Let's just experimental. What do you see? In here, you have like channel impulse response. These are very narrow pulses, something like 5 nanosecond width. And these are made, in fact, with at 1 gigahertz with a bandwidth of 200 megahertz inside an indoor area. So this is an impulse response, different paths actually. If you take the Fourier transform of that, this is the Fourier transform. Okay. This is the impulse response. This is the Fourier transform of the impulse response. Now, so in time, if you're doing wideband signaling, okay, in time, you have an impulse response like this. In frequency, you have something which goes up and down like this, and sometimes it goes again like 40, 50 dB lower than the frequency which was a little bit before that. Okay? So this is very similar to fading. Earlier in time I had fading. This is fading in frequency. Okay? So if I'm doing wideband signaling really, my bandwidth is very wide. Inside the bandwidth, frequencies go up and down. If I do narrowband signaling, inside my band, it's almost constant because it's very narrowband. It's only a portion of this, only this much. There's no changes. When I go wideband, the received signal strength at different frequency changes. And sometimes it goes very into fade. And that type of fade is referred to as frequency selective fading. Do you remember in the time? The other one was time selective fading. I had a narrowband signal. I was going 1 inch away, and suddenly at 10 gigahertz, I go 30 dB low. Huh? In wideband now, if I go like 10 hertz back and forth, suddenly my signal goes 40 dB up and down. If my signal is narrowband, I don't observe it. If signal is wideband, inside the bandwidth, I observe these fades, which are referred to as frequency selective fading. If my receiver is not smart, it kills my communication. If I'm smart, I try to take advantage. We will talk about how we can get smart after we learned about the channels. And the entire physical layer design of radio modems relies on understanding of the channel and try to avoid their harmful effects and try to take advantage of what they are doing. And that's actually the main essence of this course. First to say that how they are working, and then say that this is how people take advantage of that and design their radios. Okay, but anyways, for the time being, There is no model, nothing, just talk. So I brought this new thing in, which is, we call it wideband signaling. In wideband signaling, my time domain response is like an impulse response. Its frequency domain has frequency selective fading. This is called frequency selective fading. Okay. Now, so that's one thing. Now, one very experimental result, 200. The second thing, I told you a little bit earlier, since in here I square the magnitudes and I add them up, signal is going to be more stable. This is the same room that I showed you in here. The same room, this room. This room. Do you remember this ray tracing? This was for a cosine. Now, Koenig has done that for what? For wideband signals, like 200 megahertz bandwidth signal. In here, he just took the line of sight. I mean, first path. Here is first path and reflected paths. This is first and second reflection. First reflection, second reflection, and direct line of sight. This is direct line of sight, first reflection, second reflection, and third reflection. And he has shown the received signal strength. Wow. You want to compare it with what? You want to compare it with this. In here, when I went for direct to the second one, power was moving like that. And then after that, a little bit more, but not much. Distance power gradient, always around 2 for all of them. A little bit less than 2. Okay? Now, what happened in here? Signal became very, very stable. Very stable. But his bandwidth is very wide, like several hundred megahertz. I mean, 802.11 is 20 megahertz bandwidth, I mean, G. And then the other one, B, is like 26 megahertz bandwidth. But this is 200 megahertz. Ultra-wideband communication is like several hundred, is more than that. They have two proposals. One of them, bandwidth of each channel is 500 megahertz, which is in order of these things. The other one is like 1 gigahertz, which is like this. Okay, it's very stable. Like 802.11 is something between this one and the narrow band. Okay. GSM is like narrow band, similar to narrow for the indoor environment. So signal is very stable. How about the distance power gradient? Again the same. You see that 1.86, you remember that number. This one was 1.90, the same. So distance power gradient remains the same as you increase the bandwidth, but signal becomes much more stable. And that's the essence of like these new movements toward ultra-wideband. One of the privileges of that. Okay. But what is bad about wideband, if you go very wideband, number one, if you want to implement like a system, systems are digital. You have to sample them twice the bandwidth. So if I have 1 gigahertz bandwidth, 2 gigahertz sampling, then I want to do signal processing on top of that. It's like a speed, which brings the cost up. But these are the issues that they get compromised throughout the time. But so far as we are concerned, for the time being, for the understanding of the channel, we see that the wider the bandwidth is better. But if I want to have wider bandwidth, I have to migrate to what? Higher center frequencies. And if I move to higher center frequencies, what will happen? The power loss in the first meter increases. Okay? So if I go from 1 gigahertz to 10 gigahertz, 1 order of magnitude. So here we are. Okay, so the coverage becomes shorter. So I go to ultra-wideband, coverage is short. So who is thinking about ultra-wideband? They are thinking about new applications that we discussed in the first lecture. So like wireless USB, for example. Okay? So you have very, very stable signal, only a like few meter distance. Okay. So that's about like wideband receive signal. Now, one issue which comes in here is that if I have a multipath environment like that, I mean, I got used to this simple parameters, huh? So when I was talking about coverage, I talked about distance power gradient, which was one parameter which carries me really. That's a very complex phenomenon. But with distance power gradient, I have some feeling about coverage. Then I came to like Doppler shift. I had one parameter related to that, which was maximum Doppler shift, which was carrying me along. See, engineers are lazy people. They look for one parameter for a very complex phenomenon so that they can do something and make a living. Huh? Now we have this multipath environment. Again, we want to associate to that one number. So one number to do what? I do this multipath measurement in this building, and I go to another building is like another shape. I go outside is another shape. Huh? And how do I want to communicate that with other engineers? Huh? And so what I want to do is that I want to come up with one number. So the number for a shape like this, the first one which comes to my mind is that, okay, I take the beginning and end of this. That's the so-called multipath spread. Huh? How much this multipath is spread. That's a good one. I may use that. Huh? But the problem is that if I have this multipath spread and I mean I have one strong path in here and one very weak one in there, or I have a bunch of strong paths from here to here, there's no difference between them. And I know that if all of them are, I mean a bunch of strong paths, rather than one strong in here, a little smaller, they will have different impacts on the communication system. So I try to change it. To change it, what they do, they use a number that they call it RMS, multipath spread. RMS multipath spread actually is mathematically second central moment of this function. What does that mean? That means that first you get the weighted average of this. So I'm starting from here to here. I take everything. I give a weight of 5 to this, 10 to this, and 2 to this, etc., according to their amplitude. And then I find the middle in there. Okay? So that's the center is this, the weighted average, which is the so-called first moment of this function mathematically. So it comes up like something like this, which is average. So how do I calculate that average? Average is like this thing. Tau bar equals integral of tau f of tau theta. Okay, divided by integral of f of tau theta. This is just to normalize it. This is the area under the curve. This is the first moment. Call it first moment. First moment. This is the average, the so-called first moment or average. Average of a function. Okay. Now, then what they do actually, they don't stay with this. They go to the next one, which is average of, they call it tau RMS. If you get the square of tau RMS, this is integral of actually tau minus tau bar square of f of tau theta. Again divided by integral of f of tau theta, just to normalize it. Okay. This is the so-called second central moment. What is the difference? In here, you're weighting, if these are different paths, you're weighting them and you take the average. In here, you take, this was the average in here, you take the difference from the peak to this, you square it, and then you weight it all over the place. You take the average. That's why they call it second central moment. Second is from here. Central because it's with respect to the average. Okay. This one is like one number which tells you that how much spread you are there. It's like RMS of a voltage of a signal. RMS value of a signal. This is very similar to that. That's why they call it what? RMS multipath spread. Because these are spreads which are caused by multipath. So this is the number that they want. So now if you want to calculate it really, for simple cases, if you have a discrete system that you know all the paths, this is not very well written, but it is in the book. You can calculate tau RMS from this equation. If you have a bunch of paths given at locations, means that if I have, like for example, two paths, one is in here at location 0, the other one is at location of 50 nanosecond, and this one is like value of like 1, and this one is value of 0.1, okay? Then if I want to come to this thing, I can calculate tau RMS from a square root of tau square average minus tau average square, where tau n, or if you want to call it, is defined by tau n is defined by sigma I equals to 1 through L. This is because the equation in there is not very good. Tau sub I to the power of n beta sub I square divided by sigma beta sub I square. This is for discrete form. I equal to 1 through L. Okay? This is like how you can calculate. That's the equation which is in there. Now, if you want to apply that equation, basically this is first moment. This is like beta 1 or beta 2 in this case. This is beta 1, and this is tau 1, this is tau 2. Okay? So what you do is that for tau average, you have sigma beta I squares. This is equal to 1 square plus 0.1 square. Upstairs you have 0 times 0.1 plus times 1 plus 50 nanosecond times 0.1. This is your tau bar. Okay, this is your average tau. Okay, and then which is, I mean, this is 0. This is 50 times 0.1, which is 5 nanosecond, divided by 1.01, which is roughly equal to 5 nanosecond. So this is around 5 nanosecond is my tau bar. Okay, this is my average tau bar. Now I can calculate the other one. I mean tau square. I can average it. I can calculate that tau square average different ways. One is that I can calculate tau square from here, plug it in this equation, or I can calculate it directly from like that integral that I had. Means tau minus tau bar square times beta I square, and then sigma divided by sigma beta I square. Means that in this case equals to this tau, which is 0 minus this, which is 5 square, times amplitude of that, which is 1, plus the next one, which is beta I square. If I did not make any error in there, that's 50 nanosecond, the second one, square, times 0.1 square, and then divided by sigma beta I square, which is this number. And that way you can calculate the tau RMS square. And then you get a square root of that is tau RMS. Or you can plug it in this equation. There are different equations that you can use. 2 different versions are given in the book. And you have one homework exactly just like this to just calculate. That's your problem one, homework number one. But basically, the issue is that the first one is that this is the tau bar. See, it's shifted toward this one, which is stronger. And then difference of this one, this is square, difference of this one, this is square. Actually, this is not 50, this is 45 square. Okay, and this is square. And then you just calculate based on that. Okay. Now, that in here I made also another mistake in here in calculation. This was 2. So this changes from that to 0.5 actually. But anyways. Now, so this is the measure. So it's one single number, tau RMS. Now, well, so far I had some physical or actually some engineering meaning for distance power gradient. Engineering meaning of distance power gradient was what? I could relate it to the coverage. And I had an engineering meaning for my maximum Doppler shift. What was the engineering meaning of that? That's the rate of variation of my channel. So if I have like a adaptive system, I have to consider that this is the rate of my channel. What is the usefulness of tau RMS? The useful of tau RMS is that if you have like a basic communication system, like a binary PSK modulation, if you increase your data rate, your bandwidth increases, you will have inter-symbol interference, and after a while you don't operate. So in multipath environment, you have a data rate limitations due to multipath. Okay? Data rate limitations or, let's say, limit for basic modulation technique is something like 10% of something like 10% of if inverse of tau RMS. This is very rough engineering rule. So if you inverse the tau RMS and you multiply it by like something like 10%, that's roughly data rate that you can achieve with a basic modulation technique. So you come to indoor areas, the tau RMS in indoor areas maximum is around like 100 nanoseconds, something like that. Okay? Inverse of 100 nanosecond is what? 10 megahertz. Okay? 10% of 10 megahertz is what? 1 megabit per second. So if you have binary modulation, you have like 1 megabit per second, roughly, which was the data rate of what? First 802.11. Okay. Now, if you want to go to higher data rates, what should you do? Either you have to change your modulation technique, make it more complex, or you have to change your receiver so that receiver somehow fights with the multipath. Okay? But the use of tau RMS is that tau RMS shows you that boundaries for basic communication. It's a number which is a measure of a spread of the channel, so a measure of rate of transmission of symbols. Okay, that's a measure of that. Because the more that the channel is spreaded, the less is your symbol transmission rate in order to avoid inter-symbol interference. So basically, more or less, this is like one general idea. We will come back to that when we are talking about modeling. We will come back to that when we are talking about modem design. So this topic will come back over and over again. But if you come to an indoor area, again, back to the computer, in this figure now, in this figure what you have is you are in the center of the room. That's again the same room, and you're using the same ray tracing. You're sitting in the center of the room, okay, and then the distance between transmitter and receiver is like increasing from the center to the corners. Okay, as you increase the distance, the RMS multipath spread starts to increase. At the beginning, when this distance is like very close, you have only one dominant path. What is the RMS delay spread? Is 0. As you go away, you have more paths, and you will have more RMS delay spread. And these are what they are in there. I mean, if you want to simulate that, how do you simulate? The simulation is very easy. I mean, if I have like any of my previous examples, so I have like this one, for example, inside the building, and I had 2 robots. This was one of my examples. Okay, this was direct path, this was the second, and third path. And I could calculate this distance and this distance and this distance. So what is the impulse response of this channel? The impulse response is very simple actually. The first path, I know the amplitude was what? Was square root of P0 divided by D1. Okay, arrival time of that is how much? It's from here to here, which is tau. I mean this D1 divided by C. This is the arrival time of the first one. Usually we set this to 0, because that's the first path. Then the second path is coming through here, which is shorter. It comes like this, which is square root of P0 over D2. And the arrival time is again D2 over C. And then the third one is even weaker than that, this one. And this one is times A. A is reflection coefficient, A1 or whatever. And this is square root of P0 divided by D3 times A1. This is the amplitude. Arrival time is D3 over C. So that's as simple as that. I can calculate all of these things. Okay? So in indoor areas, I'm talking about the distances which are up to what? Up to like 100 meters, something like that. And what was the speed of light? I mean, in 100 meters, how much of this I can go? Do you remember? I mean, the delay was associated to what? Delay was how much? For 1 meter, you had how many? 3 nanoseconds. Okay? So if I have like 100 meters distance, difference between the distances, which is roughly the size of the building, I have like what? 300 nanosecond spread. But RMS multipath spread would be less than that. Would be something like 80, 90, 50, 60. Those are typical numbers which are coming out of measurements. We will have again one lab that you get actual measurements and you calculate the RMS delay spread of the actual measurements. That would be one project that we will have later on. But in this particular example that I had on the board, you have calculated all of these things from ray tracing, for example, and you have generated curves like this, the ones on the computer, like this. When the distance, transmitter is in the center and receiver just is moving away. And this is, as it moves away, multipath spread moves from the 0 up to like 40 nanosecond. Okay, the room size is what? Like from 0 to something like 15 meters. That's the distance between the two. So I'm changing the distance from 0 to 15. Multipath spread goes up to like something like 40 nanoseconds, something like that, from 0 to 40 nanoseconds. RMS multipath spread. So, okay, so these are some numbers just roughly to relate these things in indoor environment. Then, effect of angle of arrival in wideband signals, and effect of time of arrival of first path. Number one, who is interested in that? People who are using directional antenna, like MIMOs, for example. All of them are based on angle of arrival. What will happen to the angle of arrival? If I put a transmitter and receiver inside of a room, this is the impulse response. But these paths are arriving from different angles. In this particular, graph, Genning again had generated this long time ago. What he did, he was working on sectored antennas, 6 sectored antennas, which was used in wireless LANs. One of them which was designed by Altair. Now, what you do is that you're in an indoor environment, and then your receiver, this is your indoor environment, this is your transmitter, this is your receiver, and you have many, many paths between these guys. Many, many paths bounced all over between them. What you do is that you take these paths and divide them in 6 sectors. Let's see, did I divide it? 1, 2, 3, 4, 5, one more. 6 sectors, equivalent sectors. Okay, and you get these paths, they have 1 impulse response, these paths have 1, this has 1, so, but this one, they don't have anything. Okay, this is only for 3 paths. Now, if you go and you get all the paths inside this box, which was my example that Kenning was running all the time, you get things like what you see on the screen. This one is for the line of sight angle, apparently, because the line of sight is in here. These are other paths close to line of sight. This is the next one, next one, next one, next one, next one. This last one only has this small one. This one has only this. This has several, this has several, this has several. So the paths are arriving in different angles. Now the question is that how do you want to model that? Number 2, who is interested? I told you 802.11. Right now, N, they're working on that because they're working on standardizing MIMO technology. Okay. So you want to model, associate these paths to the angle of arrival. And see that these paths are arriving in clusters. This one cluster, one cluster, one cluster. How do you model the clusters then? These are the type of thing that we want to learn, how people are modeling them in the standardization activities. So modeling of this is something that we will study later, but the meaning is like if I look at different angles, I have different impulse responses. Okay. And we are interested in that characteristic. We want to model that. For what? For the multiple antenna system. Now, another thing that we are interested in is time of arrival of direct path. Direct path is first path between transmitter and receiver. First of all, this direct path between transmitter and receiver, I mean, in here I have wider bandwidth, less in here. As I'm reducing my bandwidth, these pulses are becoming more spreaded. You see that? They become more spreaded. This is highest bandwidth, middle, and this is less. As I'm reducing my bandwidth, these paths combine together. When they combine together, what happens? 2 things happens. When they combine, that phasor comes to picture. I will have multipath fading. Beyond that, when they combine, the peak is not at the time of arrival. The peak gets shifted from the time of arrival. Okay? Now, who is interested in that then? People who are working in positioning. In positioning, what they do is that they transmit a pulse and they want to know the exact time for arrival of the pulse, because then they can calculate the distance from the same equation that we were using all the time. Okay? We were using tau equals to d over c. Now they use d equals to tau times c. Okay? So that is like a new area of research, and people are trying to model that, this time of arrival. Now, what type of modeling you need? Well, one modeling is that when you have the bandwidth and you have noise, you miss the peak. That type of thing is the modeling that people use in GPS, for example. Then the other thing is that now if you make your bandwidth very wide, sometimes if you have ultra wideband, for example, this first path dies, but still other paths exist. So the first path is in here, but you think that this is the first path, for example. You make large errors in distance measurement. Okay, how do you want to model that? Okay, so this is for distance measurement. So time of arrival, just measurement of time of arrival, is for location-aware systems. And it's pretty new, like past few years. So we have a lot of programs here in WPI, and they have some programs also in University of Oulu. So both universities are very good in this, like indoor positioning, we call it. All is about modeling, taking this first path, model its relationship, so far as channel modeling is concerned, relationship between the detected first path and the bandwidth of the system and the environment around you. Means how many valve was in between or whatever. Okay, and we will see part of that in our last lecture. So basically in this part, what I told you was that I talked about wideband signaling. And I told you that, well, number one, wideband signaling, when you do it, you observe frequency selective fading. Means that suddenly inside your bandwidth, you will have very deep null. Okay? And when you go wideband, then you will have data rate limitations. That was one thing that we discussed. And then we said, anyways, we will leave those for the future. I need a parameter to represent the multipath. What was the parameter to represent the multipath? Was RMS multipath spread, which is second central moment of what? Of the impulse response of the channel. That was one thing. And then I said that, well, when you look at the multipath, some people are interested to relate the multipath to the angle of arrival, because you can take advantage of that and increase the capacity of your system or the data rate of your system. And then the third thing that we said was that with this wideband communications, you want to find or analyze the time of arrival of the direct path. And those is for people who are interested in indoor positioning in particular. I think now we can take like a short pause, and then we come and we have the last part of this lecture 3, which is the so-called wide sense stationary uncorrelated scattering, classical modeling of radio propagation. That one has a lot of analytical things that I will just go over them very sketchily.